A satellite of mass m orbits a planet of mass big M and radius r with a speed of v. The radius of the orbit is r. The satellite and the planet may be considered to be point masses with their masses concentrated at their centers. They may be assumed to be isolated in space. Show that speed v is given by the expression v squared equal to gm over r. Based on Newton's second law, F equal to ma, F is the resultant force. And for this circular motion, on the left hand side, the force is gmm over r square, and on the right hand side, A is given by v square over r. This is only true for circular motion. So in this case, rearranging the terms, we have v square equal gm over r. The mass of the satellite is small m. Determine an expression for the kinetic energy Ek of the satellite in terms of g big M small m and r. So v square equals gm over r, and the kinetic energy is half mv square. So substituting v square as a g big M over r, we end up with half gmm over r. State an expression in terms of g big M small m and r for the gravitational potential energy EP of the satellite. So the EP is given by minus gmm over r. Hence, show that the satellite in orbit, the ratio of its gravitational potential energy to the kinetic energy is equal to minus 2. So the potential energy is minus gmm over r, kinetic energy is half gmm over r, so the ratio will be minus 2. Also show that the total energy ET of the satellite is given by E equal to minus half gmm over r. Now the total energy is given by the sum of the kinetic and the potential energy. So kinetic is half gmm over r, potential energy is minus gmm over r, so end up with minus half gmm over r. The variation with orbital radius r of the gravitational potential energy of the satellite is shown in the figure. So this is the variation with orbital radius. On the figure, draw the variation with orbital radius of 1, the kinetic energy of the satellite. So this is the kinetic energy of the satellite, which is positive half gmm over r, and the total energy. So this is the minus half gmm over r. So this is a mirror image, and the value every point is half of the potential energy. As the satellite orbits the planet, it gradually loses energy because of air resistance by the atmosphere of the planet. State whether the total energy ET becomes more or less negative. Now energy is lost to the environment through air resistance, therefore the total energy must become less, so that it becomes more negative. Hence, state and explain the effect of this change on the radius of the orbit. Now total energy is minus half gmm over r. If it's going to be more negative, then the r must become smaller. Hence, state and explain the effect of this change on the speed of the satellite. The kinetic energy is half gmm over r, so when r becomes smaller, the kinetic energy becomes larger. Hence, the speed of the satellite increases. The mass m of the satellite is 1600 kg. The radius of the orbit of the satellite is changed from 4 rp to 2 rp, so become closer. Use the figure to determine the change in orbital speed of the satellite. So at 4 rp, the kinetic energy is 1.25 times 10 to the power of 9 joules. So the speed will be 1250 meter per second. So at 2 rp, the kinetic energy is 2.5 times 10 to the power of 9 joules. So the speed will be 1768 meter per second. So change in orbital speed will be final minus initial, there will be 518 meter per second.